Okay, so let us start today's session. Hello and welcome to this NPTL TS session for heat transfer course. And this is week 9 of the. So this is week 9 uh, for the TS session. And we will be discussing some problems related to week 9's course content. So let us start with some questions. Okay, so let me tell you the question and then you can try. Okay. So, given a counter flow heat exchanger, okay, say let me write, given a counter flow heat exchanger, which is used to cool oil, okay, used to cool oil, which is coming at a rate of 2200 kg per hour. Okay, and the specific heat for this oil CP value is equal to 2.5 kilojoule per kg Kelvin. And this oil, we have to cool it from a temperature of 100 degrees Celsius to a final temperature of 35 degree Celsius. Okay. And we have to cool this by using water. Okay. And the temperature of the water is nothing but 17 degree Celsius. Given that the overall heat transfer coefficient is equal to 1.5 kilowatt per meter square Kelvin. So what will be the flow rate of the, let me write the question. What will be the flow rate of water? Okay. Second bit is, what is the surface area required? And the third bit is, what is the effectiveness of the heat exchanger? Okay. Now, uh, you can presume that, you can presume that the exit temperature of water is not to exceed 85 degree Celsius. Okay. And use the NTU effectiveness method. So you can try this question bit by bit and then we can discuss about the solution. So let us see the solution. Okay. So firstly, it is given that we have a counter flow heat exchanger, and the counter flow heat exchanger is used to cool a specific liquid which is flowing at a rate of 20 to 100 kg per hour, and the specific heat is given, and we have to cool it from 100 degrees Celsius to 35 degree Celsius. And for that we are using water. Okay. And we have a temperature of 17 degree, and the exit temperature should be around 85 degree Celsius. And the specific heat of water, that by convention you know that what is specific heat, but I am writing this 4.18 kilojoule per kg Kelvin. Okay. So you can very easily calculate the mass flow rate of water by using the simple energy balance. Okay. So let us do the energy balance. Let me write. Okay. So heat that is lost by the oil will be nothing but is equal to heat gain by water. Okay. So for heat lost by oil, we can calculate by mass flow rate of oil, specific heat of oil times of the temperature difference, and that is equal to heat gained by water. So we can write that mass flow rate of water, specific heat of water times of delta T of water. Well, so mass flow rate of oil is 2200 kg per hour. So one thing you have to keep in mind that you keep the unit consistent on both the sides. So this will be 2200 kg per hour. Cp of oil is 2.5 kilojoule per kg Kelvin. Delta T is 100 minus 35. So we can write 100 minus 35. And this difference is in degree Celsius. This is equal to the mass flow rate of water. Cp is 4.18 kilojoule per kg Kelvin times of this is 85 minus 17. And this is in degree Celsius. So you can see you can cancel this with this unit, and both these units are in degree Celsius, so both of them are also cancelled out. So your mass flow rate will be coming out in kg per hour. Okay, so if you simplify this, you can get your mass flow rate of water to be around 1257.74 kg per hour. So this is your first part of the question. Now, the next step is to calculate the surface area and the effectiveness of the heat exchanger. So, let us try to do this part. For this, we have to use, here it is specified that we have to use the NTU effectiveness approach. Okay, so let me write it. If you remember, the effectiveness which is denoted by epsilon, if you write it in effectiveness NTU method, then this effectiveness can be computed following the expression for, like there are two expressions if you remember. One is for co-current flow, one is for counter current flow. Okay. And that depends on two parameters, that is the NTU and the capacity ratio. So the expression, if you remember, nothing but 1 minus exponential of minus NTU 1 minus C 1 minus exponential of minus NTU 1 minus C whole divided by 1 minus C times of exponential of minus NTU 1 minus C. So this is the effectiveness NTU method for, let me write, counter flow. Okay. So here, if you remember, NTU is nothing but the number of transfer units and C is nothing but the capacity ratio. Okay. So let us first see what is the capacity ratio. That C capacity ratio. Okay. Is nothing but C minimum by C maximum. Right. So let's see. Let us for calculating this C minimum and C maximum, we have to multiply the specific heat capacity with that of the mass flow rate, and then we can obtain which is the minimum and which is the maximum. So let me write this is C for the cooler side, that is for water. Okay, let me write. So that is m dot of C times of CPC. So m dot of C is nothing but 1257.74. So 1257.74 times of CPC, which is nothing but 4.18 kilojoule per kg Kelvin. So multiplied by 4.18. Okay. So if you multiply this, you will be getting 5 to 57.35. So if you see, this is kilojoule per kg Kelvin, and this is in kg per hour. So if you multiply this, okay, you can see you will be getting unit of kilojoule per hour times of Kelvin. Similarly, you can calculate the thermal capacity of the heated oil side to be m dot of H times of Cp times of H, which is nothing but 20 2200, and this is 2.5. So this is 2200 times of 2.5, which is nothing but uh, so this is 22, so 12.5. So 125 right? 1 2. Sorry, 2.5. So 22 44. So this is so this will be 5500 kilojoule per hour Kelvin. So you can see that the minimum thermal capacity is uh, you see this has a high thermal capacity, right? And this has a low thermal capacity, correct? So now you can just take the ratio, okay? And let me do it. So if you take the ratio, you can get this to be 1.046. So this is about C, but we have to calculate the NTU of the effectiveness method. So for that, we have to first calculate the effectiveness, which is nothing but TH1, okay, minus TH2 divided by TH1 minus TC1. Okay, so this is for the counter current flow. So TH1, if you see, this is nothing but 100, and we have to reduce it to 35. And similarly, we have 100, and TC1 is 17. So if you substitute this, you will be getting 0.783. Okay. Now, since you know the effectiveness now, you can substitute here. You see, effectiveness is equal to 1 minus exponential of, if you remember, I have written this NTU, 1 minus C whole divided by 1 minus C times of exponential of minus NTU 1 minus C. So this is equal to, now you got 0.783. Okay. So you can little bit modify this expression before substituting that. Let me do that. So if you multiply this side, you will be getting, say, epsilon minus epsilon C exponential of whatever terms you have. This is equal to 1 minus exponential of what are the terms that you have. So you can take this common. So you can do it. So epsilon minus 1, and take this to that side. So this will be epsilon C minus 1 times of exponential of the terms that. that we have here. So this implies what we have. We have epsilon minus 1 divided by epsilon c, epsilon c minus 1. And this is equal to exponential of minus times of NTU 1 minus c. Correct? And now to find out the NTU, you can take log on both sides, which is the natural logarithm. Epsilon minus 1 divided by epsilon c minus 1. This is equal to, so this is minus, this is NTU 1 minus c. So you can substitute the values. Okay, so this is minus ln of, so epsilon is nothing but 0.783. So 0.783 minus 1 divided by 0.783 times of 1.046 minus 1. And this is equal to NTU 1 minus C is 1.046. So if you simplify this, you will be getting NTU is equal to 3.84. Okay. Now, if you know this, if you substitute this definition of NTU into this equation, that is nothing but NTU is equal to overall heat transfer coefficient by A divided by C minimum. Correct? So this implies you can write 3.84 is equal to the overall heat transfer coefficient is how much? Overall is 1.5 kilowatt per meter square. So 1.5 kilowatt per meter square Kelvin. Kilowatt per meter square Kelvin. Okay. Times of the area divided by C minimum. C minimum was how much? Is 5257. Okay. So we can substitute it here. 5257.35 kilojoule per hour Kelvin. So we can convert this to from hour to seconds. So that will be coming here as 3600. Okay, so you can get 3.84 5257.35 whole divided by 1.5 times of 3600. This will be in your meter square. Okay, so you can calculate this value. 3.84 times of 5257.35, 1.5 times of 3600. So this is coming to be 3.73 meter square. Okay, now let's move on to the next question. Consider that the home air conditioning system uses a counterflow heat exchanger. Okay, so let me write. So we have a home air conditioning system which uses counterflow heat exchanger. Uh, so this is using a counterflow heat exchanger to cool zero point 0.8 kg per second of air from an initial temperature of 45 degrees Celsius to a final temperature of 15 degrees Celsius. So this cooling is achieved using a stream of cooling water that enters the system at a rate of 0.5 kg per second flow rate and at a temperature of 8 degrees Celsius. Given that the overall heat transfer coefficient is equal to 35 watt per meter square Kelvin. So you can similarly calculate what is the heat transfer or the heat exchanger area. Okay. So this is the first bit of the question. The second bit is if the same airflow rate is maintained, same airflow rate is maintained, while the water flow rate is reduced to half. What will be the, or what is the percentage reduction in heat transfer? You can similarly use a effectiveness NTU approach. So again, you can try this and then we can discuss. You can do one thing. You can take it to be 0.75. Okay. So let us see the solution. So for the first part, the heat exchanger area, you can follow the same procedure as we follow in the previous question. So it's exactly the procedure is very similar. You can calculate the NTU and then the required heat transfer area. Next is we have to see if the same air flow rate is maintained while the water flow rate is reduced to half. What is the percentage reduction in heat transfer? So let's say the mass flow rate, it is reduced to half of 0.75. Okay, because the water flow rate is reduced to half. So 0.75 divided by 2, which is 0.375 kg per second. So we can calculate similarly the C, okay, which is C, which is nothing but we have the for the cold side the mass flow rate and the specific heat. So this is 0.375 times this is, we can write it as so this is 4186. Okay, so will be 1569.75 watt per Kelvin. Right? Again, for the air side, that is the heated side, we can write it as the CH, which is it will be remaining same as previous, that is zero point 0.8 times of the specific heat for air, that is 1005. So this will be around 804 watt per Kelvin. So next step is to calculate C, that is C minimum by C maximum, which is you can see here 804 divided by 1569.75. So this will be around 0.5122. And NTU is equal to U times of A divided by C minimum. And you can again use the epsilon NTU method, that is 1 minus exponential of minus NTU 1 minus C. Okay. Now NTU you can calculate from the previous part. Okay. So if you remember how we calculated that, so uh, you see, if you see the expression for NTU here, you can see the overall heat transfer coefficient is given, that is 35. This area of heat exchanger that you can calculate from the first bit, just how you calculate it. Let me write it here, how much you will be getting. So you will be getting 44.10 meter square, following the same procedure that we have done previously. If you do everything, you will be getting this area. So you know, A you know, C minimum also you know. So the NTU, if you calculate, it will be coming to be 1.92, and that will remain same because you see the overall heat transfer coefficient in this case you are not changing. The area that you obtain from the first part, here the same heat exchanger area is used because you see only the flow rate is reduced by half and you have this C minimum. Okay. So the NTU will be same as the original situation. So now if you substitute this value of NTU, you can get the epsilon value, that is to be equal to 0.76. So now if you see, this epsilon for counter current flow is nothing but TH1 minus TH2 divided by TH1 minus TC1. Okay. So this epsilon is nothing but 0.76 from here. Okay. And this is the temperature difference for the hot side. And this is nothing but TH1 minus TC1, that we already know because we have 45 and 8. Okay. So this is 45 minus 8. So the decrease in temperature for the hot side of the or the air side of the fluid is nothing but 28.12 degree Celsius. So now the percentage reduction. So you can see if the mass flow rate is reduced, then the heat transfer should be have been reduced. So now initially it was 30 because you can see this is 45 and 15. So initially the difference was 30. Now the difference is 28.12 divided by the initial, that is 30. So if you calculate this, this will be 0.0627, which is nothing but 6.27%. So this is the percentage reduction that we can see in heat transfer when the when the mass flow rate is reduced to half. Okay, let's do the next question. So, given a fuel oil, okay, let me write. So, given a fuel oil is heated at a rate of 1.3 kg per second through a annular double pipe heat exchanger. And it is heated from 20 degrees Celsius to 30 degree Celsius. And it is heated using water which is coming at a temperature of 70 degree Celsius. Okay. And for the double pipe heat exchanger, the outer diameter is 2.13 centimeter and the inner diameter is 1.86 centimeter. Okay. And this is for the water side. Okay. And it is flowing through the, let me write. So this water is flowing through the through a copper tube at given velocity of 0.76 meters per second. Okay. Uh, Hold on. So this water is actually flowing through a copper tube and this copper tube has this characteristics. Okay. The second thing is this oil, fuel oil, is passing through the annular region formed by the inner copper tube and outer steel pipe. Okay. So this fuel oil is actually passing through the annular region okay between the copper tube and outer steel pipe. So let me write. Uh, so this has a outer diameter of 3.34 centimeters and inner diameter of 3 centimeters. Some additional informations are given. One is the fouling factor for the water side. So let me write fouling factor for water side. And another we will be having the fouling factor for oil side. So this is equal to 0.0004 meter square per sorry meter square. The fouling factor for the oil side is given to be 0.0009 meter square Celsius per watt. Okay. So let me make this little bit smaller so I can add more informations. Okay. So these are some of the properties that are being provided for water and oil. Okay. So we have kg per meter cube. Okay, then this is 980 and this is 850. So this is nothing but the densities. Then we have specific heat capacity in kilojoule per kg degree Celsius. This is 4.2 and this is 2. Then we have thermal conductivity in watt per meter degree Celsius. This is 0.7 and this is 0.038. And we have the velocity to be meter square per second, which is 4.2 and 7.5. So here you can neglect the resistance of the copper tube. Okay. Because copper is highly conductive. Okay. So calculate the length that is required for this heat exchange. So length of the heat exchanger. So you can give it a try and then we can discuss. Okay, so let's start solving this question. So first you need see in unlike previous questions here mass flow rates are not given. So let's start with calculating the mass flow rate. Okay. So you can calculate the mass flow rate for the water side, which is nothing but density times of velocity times of the area. So density is 0.98 and the velocity is 0.76. So this is 980, 0.76 times of the area, that is pi by 4 times of. So you can see the inner diameter is 1.86. So we have 1.86 centimeters. We can convert it into meters square. So this is nothing but 0.199 kg per second. Now we can do this again. The heat that is lost is nothing but by one fluid is nothing but heat gained by the other fluid. So this implies we can do the mass flow rate of water. So this one times Cp of water, and we have this Thi minus inlet minus outlet. This is equal to m dot of O, Cp of O. This is oil. Okay, on the output side, outlet, oil on the inlet side. This is nothing but, so we can consider this to be 0.2 almost. So this is 0.2. Cp of water is 4.2, and we can do 10 to the power of 3 because it is in kilojoule per kg. So, and this temperature is, you can see, okay, this is 70. You can see the inlet is 70. So 70 minus THO, this is equal to, for the water side, so this is equal to 1.3 times of 2 point, this is given 2, right? So 2 times of 10 to the power 3. And the temperature you can see for the oil here at 20 to 30. So 30 minus 20. So if you calculate this, you will be getting THO is equal to 39.05 degree Celsius. Now you can calculate the log mean temperature difference, that is LMTD is equal to, you can write theta I minus theta O divided by log theta I minus theta I by theta O. So theta I, as you can see, is 70 minus 30. Okay. Minus, you can do 39.05 minus 20 and divided by log 70 minus 30 divided by 39.05 minus 20. So this is equal to, if you solve it, you will be getting 65.02 degrees Celsius. Okay. Now let's see for the water side. For the water side, we can calculate the Reynolds number. Okay. So Reynolds number for the water side is equal to the diameter average velocity divided by mu, that is the kinematic viscosity, which is given here. Okay. So this is 0.0186. That is, it is given 1.86 centimeter times of the average velocity, that is 0.76, that is also given in the question, divided by the kinematic viscosity. For the water, it is 5 times of 10 to the power of minus 7. So you can, it is given 4.2, you can take 4.2. So you will be getting around 28.27 times of 10 to the power of 3. Next, you can calculate the Prandtl number. That is Cp we have rho V Cp by K. So this is nothing but 980 times of 5 times of 10 to the power of minus 7 times of 4.2 10 to the power of 3 whole divided by thermal conductivity. You can see 0.7. So this is equal to 2.94. So you can calculate the average heat transfer coefficient by using the DTS-Boelter correlation, that is the Nusselt number to HI di by K, which is equal to 0.023, Reynolds number to the power of 0.8, Prandtl number to the power of 0.3. So there are two things you can see. Okay. Yes. So we can calculate the Nusselt number. Okay. This is, you can substitute these values. This is equal to 0.023. Reynolds number is 28.27 to the power of 10 to the power 3 to the power of zero point 0.8, and Prandtl number is 2.94 per 0.3. Okay. So for calculating the average heat transfer coefficient, HI, you have to multiply with K by DI, which is nothing but 0.7 divided by 0.0186. So if you substitute everything, you can get the average heat transfer coefficient to be around 5025.23 watt per meter square degree Celsius. Okay. Now let's calculate it for the oil side or the, okay. So for the oil side, however, we don't have a cylindrical cross section. We have an annular cross section. So let me write oil side. So in this case, we have to use the equivalent diameter concept. Okay, so first we have to calculate the equivalent diameter. So this D equivalent is equal to, we can write 3. So this is 3 centimeter. So if you remember, you can calculate the equivalent diameter. That is 2.13. This is nothing but 0.87 centimeter. And then you can move on to calculate the Reynolds number, which is nothing but, if you remember, rho VD by mu, but here we can change it to times of G divided by A. Okay. Where this G is the mass flow rate per second. Okay. And this mu also you can substitute with, so dE divided by, instead of mu you can replace it with rho times of V, and then this is G by A. So this is equal to 0.87 times of 10 to the power of minus 2 divided by 7.43 times of 10 to the power of minus 4 and multiplied with 854. And again with G by A, that is 1.3 divided by pi times of 0.03 square minus 0.213 square. So this is equal to 5081.8. And similarly, you can calculate the Prandtl number, which is rho VCP by mu K, which is again, you know the density, you can substitute 2 times of 10 to the power. So the 850, which is the density. C is the 2 into 10 to the power 3 is the specific heat capacity. And then we have 7.5 times of 10 to the power of minus 6 divided by the thermal conductivity, which is 0.038. Okay, which you can find out. So now you have to calculate the average heat transfer coefficient, that is referred to the outside surface of the copper tube. Okay. And in this case, you have to include the fouling factors as well. So that is, we can find out the sum of the total resistance, that is 1 by U, is nothing but D0 by Di times of 1 by Hi plus D0 by Di times of Fw. Okay. Plus 1 by heat transfer for the outside plus F. Okay. So you can just simplify this to be d0 by di times of 1 by hi plus fw plus 1 by h0 plus a4. So now you can substitute all the values. Okay. So this is nothing but 2.13 divided by di is 1.86. 1 by hi. Hi is 50. 5025.23 plus this fouling factor is 0.0004 plus 1 by HO. So HO similarly you can calculate. I have not shown here, but you can calculate by yourself. Okay, from here, like Prandtl number you can calculate, and again you can calculate HO. So HO will be 1750 plus we have 0.0009. So this will be equal to 0.00215. So this implies if you take the inverse of 1 by u, this is 1 by 0.00215. So you will be getting the overall heat transfer coefficient to be 480. Watt per meter square degree Celsius. So Q you will be getting UA times of LMTD, that is the log mean temperature difference, which is equal to U times of I D0L times of LMTD. So first we have to, for calculating this L, we have to calculate the heat. The overall heat transfer coefficient we now know, LMTD we have calculated, pi D0 also we know. So we have to only, here we have to calculate this Q value. Okay. So first we have to calculate Q. So what is Q? Is we know that it is the heat gained by the heat that is gained by oil. So it's nothing but m dot Cp delta T, which is 1.1 times of 1.884 times of 10 to the power of 8 times of delta T, which is 20 minus 10. So this is equal to 20700 watt. And now substituting this Q value, we have 20700. This is equal to U is 480. Then we have pi. D is 2.13 divided by 100 times of L and LMTD. So LMTD we got how much? 65.02. So if you simplify this, you can get the length of the double pipe heat exchanger to be approximated to be more or less 15 meters. So I hope you understood this problem as well. Okay, before closing the session, we'll do one simple problem and then we can close this session. Okay. So as we discuss here that we use this uh, equivalent diameter concept. So we'll do one simple problem to get that fundamental clear. Okay. So consider a double pipe heat exchanger with its inner diameter and outer diameter of 4 centimeter and 5 centimeters respectively. Uh, so this is for the inner pipe. Similarly, for the outer pipe, we have the inner diameter is equal to 10 centimeter and the thickness that we have for the layer is equal to 1 centimeter. Then what will be the equivalent diameter of the annular region? So if you remember, the hydraulic diameter or the equivalent diameter is nothing but 4 times of the area divided by weighted perimeter. So area is nothing but pi by 4 times of d out square minus d in square whole divided by pi times of d out plus d in. So you can see this 4 and 4 will be cancelled out. This pi and pi will be cancelled out. So this is equal to, we are left out with d out square minus d in square divided by d out, this d out minus plus d in. And you see this you can replace with a square minus b square formula, that is d out plus d in. So d out plus d in minus, so the plus part will be cancelled out, and you can directly write that the dh is equal to d out minus d. So this is what we did here. You can see, for when we calculated the hydraulic mean diameter, in this case, we did the same thing. Okay. This is how we calculated the equivalent diameter for the annular region. So let us complete this. So if you substitute the values, you can get d out is 5, d in is 4. No, sorry. This for the annular region, if you see, this is the inner diameter, this is the outer diameter. So this is something like this, with this some kind of thickness, and we have another with some kind of thickness, that is 1. So the inner diameter what we have for the larger is 10 centimeter, and for the inside one we have this as 5 centimeter. So the difference is 10 minus 5. So d out is 10 centimeter minus 5. So this will be 5 centimeters. So this is how we calculate the equivalent diameter. Okay, so this is what we have used. So I have made this explanation again so that it will be clear. And similarly, we have used this concept of fouling factor here. Okay, so and therefore we can do another simple understanding of this fouling factor so that it will be much more useful. So if you have, the heat transfer coefficient is known for the outside of inside, then the overall heat transfer coefficient is given using this 1 divided by H0 plus 1 divided by Hi plus whatever the fouling factor you have, or we can also write this as resistance due to fouling. But also, if this fouling factor is given, per meter square or some unit, then you have to multiply with the area to get the overall fouling factor for the heat exchanger. Okay. So I think all the concepts that have been taught we have discussed today. So I hope you enjoyed today's session, and we will meet again next week, same time, to discuss more problems related to next week's course content. Till then, you can practice more questions, and so meet you again next week. Thank you.